Professor Hong got his BS bachelor degree from our department in 1982, and got his PhD from the University of California at San Diego in 1988. And in 1992, he went back to National Tsinghua University, and he is a professor in National Tsinghua University now. And today's talk is, you can see here, the physics behind breaking the bamboo chopsticks. Let's welcome Professor Hong.
So where are you from?
India.
Do you use chopsticks? No, you use hand.
Yes.
Oh, okay, right, all right. So first, apologies. So some of my transparency are written in Chinese, but I'll speak in English, so you shouldn't have problem following. All right, so this is a talk based on actually today's talk are based on two papers that we got accepted this year. So the bamboo chopsticks will appear in PRL, and another talk, you will see another one from PRE, right? And to whet your appetite, so you wonder what has bamboo chopstick to do with the shark? I mean, this is Nemo, and what has it to do with chopsticks, and what has it to do with spaghetti? Okay, so that's just to whet your appetite, and that's the selling point of this talk. Right, so as a rule for the talk, please interrupt me at any time, really, at any time, interrupt me. What? Just interrupt me if you have problem. Right, okay. So Christmas was the two days before, so here is a card for the festival, and so that's oops. Right, so I think that's a good card. So that means somehow you have to jump out of the box. Okay, Santa is not always a good guy, right? So you don't need to be good and nice. Right. Here we are. And one reason for doing this project is because Tsinghua has a rival called Jiao Tong University, and every year they have a competition, and the competition is called Prom and Bamboo. And Tsinghua, where I'm from, we are prom. And Jiao Tong is bamboo, so we want to break their spirit. So that's why we need to break the bamboo chopstick. Right. Okay. So that's one motive. Right. And is there anyone from Jiao Tong? No. Oh, oops, sorry. Okay. Whoops. Right. Okay. So that's just for fun. And so as usual, I mean, because my training in San Diego was on theories, but this talk will be mainly on experiment, and I know nearly zero on experiments, so all my knowledge are from my collaborator. And for this talk, my collaborator are mainly the red one, okay? So a lot of them are from the Institute of Statistics, and that's not statistical mechanics, okay? It's mathematical statistics. And some of them are from Taiwan in Department of Geography. And some of them are from neuroscience. And so, right, okay, so here are, oops. Okay, so here's the introduction. So the introduction will be, I will give you an idea why we got interested in the breaking of bamboo. And the reason is, in the past 8 years, we've been doing crumpling, okay? And what is crumpling? What is crumpling? Crumpling, okay? So this is crumpling, okay? And so you may ask, why do we want to do this? And as you can see, this is the paper, crumple paper, and this is also crumpling, and this is more relevant to anyone who has a car, okay? And this is also crumpling. Why? Because if you look at a large scale, the mountain and valley they are a result of the movement of tectonic plate. Okay, and of course, the main reason for having a mountain and valley are volcano activity. But the second most important factor are crumple, because these two things, they collide. Okay, so that is also crumbling, and so crumbling. So the conclusion is crumbling. Interesting. So we start with something easy and simple, and oops. Okay, so I'll give you a review of my background. So if there's anything that you're interested or you have any idea, so just contact us or we can have collaboration. So starting from 2008, so about 6 years ago, I recruited a few students who are interested in this kind of problem, which we call it soft matter or nonlinear physics. And so in this work, we did a MD simulation, molecular dynamics simulation on granular particle. So that's one background, and as you can see, the molecular dynamics simulation is one weapon that we often employ in our work. Push. And that is another simulation, but this is simpler than molecular dynamics. And what that is, crumpling, instead of a piece of paper, this is a crumple of a piece of wire. So it's a one-dimensional object, and that can mimic to the potent folding. Okay, but in this case, as you can see, we have two plates, so it's two-dimensional crumpling of a wire. Okay, and because limit of time, so I'll do it quickly. And this is crumpling of a piece of paper. Okay, in 3 dimensions. So if I think most of you are graduate students, so you wonder why things like as simple as that, how can get to a physics review letter so you can read it? Okay, it's simple. And the first student is a sophomore. No shit. Okay, no kidding. It's a sophomore. Okay. So means this kind of problem, they are simple. Okay. So as long as, because they are so familiar, so if you can find anything unusual, no matter how small, people are very interested in it. Okay. So that's the fun of doing this kind of project. And the reason why we have all this is just to sort of brag, because I can't do experiments, so being able to build all this high pressure chamber, that is sort of a big success. And this is also paper, okay? But in this case, we collaborate with a synchrotron radiation center. And why do we want to do that? Is because we want to know the internal structure of a crumpled sheet. But you ask, you don't need to use synchrotron, you can just cut it open in half. But that is invasive, okay? We want to have something that you can look at it and then you can continue to crumple it. You want to know a continuous evolution of the structure, so you want to cut it open. Okay, so in that case, synchrotron radiation, that is a very good weapon to do that. And so that's one thing. And so that's in PRE, and this thing got quite a few advertisements, for instance, from Physics Today, okay? So they like this work, so they feature this work. And that is another work also on crumpled sheet. And what we found here is when you take a crumpled sheet and cut it in half, you see there's many domains. What do I mean domain? That means if you cut it in half, you see all these cross sections, they tend to be parallel. Okay, so these are parallel. In here, they are parallel, and that mimic the liquid crystal. Okay, so that captured the attention of the editor. So they think that's cool. Okay, so they get to the front page, cover page. So again, Li Yanzi is a senior, and Tzay-Ming is a senior. Okay, so they are all undergraduate. Okay, and Li Yanzi later went to Cornell, and Tzay-Ming went to Princeton. Okay, so being able to publish PRL for undergraduate apparently is a big boost for them. So they all went on to very good school. Question? Okay, please interrupt me. And that's another PRE. In this case, we crumple the piece of paper, and the pressure we apply, and this is density. So apparently, the more you apply the pressure, the smaller the ball will be. Namely, the density will get higher. So you can plot, and you can get all sort of phase diagram. And that's by this guy. And so that's a senior, and he's now in MIT. Okay, so Bai Wubin is a senior. And that's another simulation. This is, again, molecular dynamics simulation, but I will not bother you with that. Okay, so that's from last year. And because we have experience with crumpled paper, so the National Palace Museum, so it makes me feel like 很有学问, okay, National Palace Museum. So they asked us to solve a problem which they have encountered for at least 2,000 years. No kidding. And what is that problem is, I think, I'm not sure about India, but in Egypt, in Japan, in Korea, in China, most painting or calligraphy, they are written on a scroll. Do you know scroll? 卷轴. When you open the scroll, something like that, very often, the long side, they would curl outward. They'll curl outward. So that's a problem which they hate. Firstly, it's ugly. And secondly, when it curls upward, there are tension on these two sides. So the paper tend to, the fiber would tend to get torn, and the pigment tend to fall off. So it's a serious problem. So in this case, we sort of solved the problem. And so that's also get to PRL and got selected. And what else? And okay, so filter, they also feature that. And science also features that. So that's shameless propaganda. Okay, anyway, right. So here we are. And that's called power law relation. So in the previous work, we deduced a lot of power law relation. So what do I mean by power law? Power law means if you have y as a function of x, and you plot it in log plot, you become a straight line. It's called a power law. Do you see what I mean? So if you log plot, if the data look like a straight line, it's called a power law, and it's special. Okay? So if the slope is minus alpha, so that says y is proportional to 1 over x to the alpha. Okay? And it's a very special relation. And if you have never heard about power law relation, you should check the Wikipedia. Okay, Wikipedia will tell us that there are more than 1,000. Oh no, I'm sorry, I'm kidding. More than 100 instances in nature and in man-made phenomena that exhibit this. Okay, power law relation. Okay, and so what we did in this problem, so that's accepted by, it hasn't been published, so it doesn't have a number. So in this case, we are doing this. We crumple again. We crumple a sheet. So instead of measuring the force, we measure the sound. Okay, and everyone knows this sound. I mean, this is something you hate. Okay, when you go to a cinema, someone was open the candy wrapper, or someone reaches his hand into his bag for a hamburger. Okay, that's a noise, crumpling noise. Okay, and what's special about that is if you measure the noise, you can measure the intensity of noise, and you can do a plot. X-axis will be the intensity of the noise. So that's a small noise, that's a medium noise, and that's a noisy noise. And y-axis will be the number of the noise. And it turns out there are a lot of small noises and very few big noise. So it decreases monotonically. Okay, but we plot it in log plot that look like that. Okay, so it's special. And what makes it even more special is earthquake obey similar law. And I don't know India, but in Taiwan, in Japan, people are afraid of earthquake because we are on the verge between tectonic plates. So people are very interested in power law. So the idea before this talk is people try to understand the origin of the power law for earthquake by studying this. Okay? Okay, so if you're not, then I'll tell you later that this is wrong. Why this is wrong? Okay. So that's the point of this talk. Okay. So before we do this work, people already know that the noise, the crumple noise, a very power law. Okay. So when we start this project, we try to do something different. So what did we do? Anyone has a plastic bag? Anyone has a plastic bag? 有没有塑胶袋？有没有不要用的塑胶袋？借我一个。垃圾桶，有没有垃圾桶？啊，我听到塑胶袋啊，谢谢。Thanks. So it turned out that when you crumple a paper, the noise is a very power law. But when you crumple a plastic bag, you also get a power law. But alpha is different. Okay? It's different. So when we start this project, we take out a new piece of paper. Okay? And we put them together and then crumple them together. So the idea is there are interaction between these two. So because individually, they are of different exponent. So naively, you expect when you crumple them, they would not be a power law because they would at least two turns. But of course, you would expect because of interaction, you probably will get a power law, then you get a PRE. That's the idea. Okay? So we do the experiment, and we measure the data, and it turned out to be like that. Okay? So we said, wow, that's very good. So interaction somehow sort of merge these two materials into sort of a magic power law. But it turned out everything is wrong. Okay, why is that? So I'll tell you the story. Right, so let me see. So power law, so that's energy. So that's small noise, medium noise, noisy noise, and that's a number, okay? So let me show you why this is wrong. So to review, so this is power law, okay? So before you take a log, it looks like something like that. When you take log plot, it becomes a straight line, and the slope will be the exponent, okay? So that's power law. And let me give you a walkover of different power law. So in this case, that's where the NEMO comes in. So you can see that's a two Nature paper. And what they did is they put a GPS on shark and whale. So it has to be the fish or the animal that on the top of the chain. 它必须是猎人，是专门猎食的。And they monitor how far they move. It's every 1 hour or 2 hours, okay? And it turned out, so you would thought that they would go like a random walk, okay? So if you record their displacement for each hour, you thought they would go like random walk. So the distribution would look like a Gaussian. But it turned out, it looked like a power law. Okay, you see, so what? Okay, so what? So that's a two Nature paper. Okay, and the reason behind it later they find out is because for shark or tuna fish, they don't do like that. Most of the time, they do like that. They would just go here and there and eating fishes. But once the small fish got exhausted, they would do a very long walk to a next place. Okay, so that means there's a high probability of doing a very long walk. And because of that, the distribution becomes a power law. Okay, and it's called Levy-Fried. Mathematically, it's called Levy-Fried. Okay, so in this case, the foraging patterns of fish or mammals in the sea, they don't follow a power law relation. They don't follow a Gaussian, but instead a power law. So that's one instance. Okay, just bear in mind, and that's Nature paper. And in the end of this section, I'll tell you they are all wrong. Okay, so bear in mind. Okay, so that's one of the 100 instances of power law, very famous. Okay, that's Nature, and I'll give you more examples from Science and Nature. Question? Right. And that's stock market fluctuation. And this guy from Nature, and that's the famous Stanley. Stanley has been in Taiwan 2 or 3 times. He's in University of Boston. And he found that the stock market fluctuation. So you can have small fluctuation, you can have big fluctuation. So in this case, small fluctuation happen every minute, every second. Big fluctuation or crash, very rarely. And when they do it over, I don't know, 20 or 30 years, they claim to find a power law. Okay, and that get on a Nature paper. Okay, so that's another instance. And also, in the end of talk, I'll tell you this is also wrong. Okay, why? So you need to hang on. Okay. And that's earthquake. Yeah. An earthquake is called a GR law, and you can recognize this famous. Okay, because earthquake is all measured in Richter scale. Okay, so that's old Richter, good old Richter, and they found that the earthquake also obey a power law with the exponent roughly equal to 1, namely the occurrence frequency about go inversely proportional to the magnitude. Okay. So, okay, but I mean that's probably the most important law in地震学怎么讲 seismology, yeah, the most important law in seismology, and it turned out also need to be revised from. And that's forest fire. And so for forest fire, so that will be for each fire when it started and when it distinguished how many acre it affect. So small forest fire, medium, and devastating California forest fire. And it turned out also look like a power law. Okay. So that's and this is relevant. Okay. So ladies, you will look at that. That's a Romeo and Juliet. Okay. And what is that called? Zip law. So Zip is this guy. He's a professor of linguistics in Harvard in probably 1930 or something, and he died very young. Okay. He found that we take a book, for instance, the most classic book is Moby Dick. If you take a book and you count the numbers of words on it, okay, and you count how many times each word occur, so the number 1 will be THE. So that's the most frequent occurring word, and the second one is off, and the third one is and. Okay, so x-axis will be the rank. So THE will be rank number 1. Off will be rank number 2, and y-axis will be the number of times it occurred. Okay, and it turned out also a power law. Okay, and so they check Romeo and Juliet and check Alice in the Wonderland. Okay, or they even check Bible, and they even check classic from other country, from other culture, and they always find power law, and so that's very strange. Okay, a power law. Okay, question? Okay, power law. It's called a zip law. And you can check in YouTube. There's a very good YouTube. It's called a Zip's Mystery. I strongly recommend that, and it's very fun. Okay. So, but Zip, before he died, he never proposed a theory why that is. So this is sort of an empirical law, and up to today, no one really knows it. Okay. But about 10 years ago, there's a guy called Miller. So Miller, he did an experiment. He just randomly picked a word. For instance, you have 26 alphabet, A, B, C to Z, including a space bar. So you just randomly type it, okay? Every time when you hit a space bar, so that's a termination of a word. So you just do that. You just type, I don't know, 100,000 words. And he analyzed this law. It turned out also look like a power law. So that's this picture. Okay, so it says monkey, so he called it Miller monkey. Okay, so he said if a novel was typed a monkey, you also have that. Okay, so it's no big deal. But that's 10 years ago. But soon after Miller proposed his monkey theory, people discovered that in real literature, except for the zip law, they are the same, but other distributions are very different. Okay, and that's easy because when monkey type word, most words it doesn't make sense. Also, there's no grammar. Okay, so the Miller monkey theory was overthrown. So up to today, people still don't understand why the literature, they would obey that. And one hint is probably that. Okay, so he guessed. He said that when you write something or when you try to speak something, you try to make the least effort. So that is very similar to least action in physics, in mechanics. You try to save your energy. You try to use the fewest word to express your thoughts. That's the conservation law. And the second thing is they are structure. So for word, apparently they are grammar. Okay? So I think these two things combine to give the zip law. Okay? And it turned out in our work, we found that this is also not a power law. Okay, so a lot of power law got shot. I mean, got overthrown by our analysis. Okay, let me see what else. Okay, and that's a very famous Pareto distribution. Anyone know that? Pareto or 2080 law? Anyone heard that? So that says the property of a society, of a city, of a country, or of the world. So that's the rich man, the red one. The yellow one are the poor man. Okay? So that means 80% of the treasure are owned by 20% of rich guy. So it's called 80-20 law. Okay? And the distribution is also 80-20 law. Okay? And it's also a power law. Okay? And for that picture, it says the hamburger got consumed each year. They're actually being eaten by just 20% of the population. Okay? So people, I don't know how to come up to that. Okay? And that's Pareto. It's Italian. Question? So you can see a lot of power law. There are more examples. For instance, the activity of solar flare also obey power law, and the size of crater or moon also people report obey power law. And the criminal record, if you go to a jail, they are heavy criminal, they are light crime. So if you check how many crimes each prisoner commit, okay? So commit one crime, commit 10 crimes, commit 1,000 crimes. It turned out, and this is how many prisoners. It turned out also look like a power law, okay? And you can see these are English cities, and y-axis is the population, okay? So London is more populous, and Birmingham leads rank second and third, and you can see it looks very much like a power law, okay? And Faubourg, you can check the surname, okay? Check how many people share the surname. So the number one most popular surname, how many people, okay? And people also claim that it looked like a power law, okay? So a lot of power law, okay? So now physicists, they start to wonder, if there are so many power laws, probably there are universal law. Okay, physicists love that. Okay, a universal law, one law shoot everything. Okay, in Chinese 就是孔老二什么一道一贯之，咻，可以吗？就一个就把所有的都打翻。So there are many theories, and that's one popular theory called SOC. Okay, not system on chip. Okay, it's a self-organized criticality, and that's based on senpai. So what is senpai? That means if you sprinkle the sand continuously on a senpai, you get avalanche of sand of different sizes. And you can keep a record of the avalanche. Small avalanche, medium avalanche, big avalanche. How many times you record, okay? It turned out to be a power law. And this is the guy called Tabat. And he claimed that this is the law that governs all the power law in nature. So this is the book. So you can see the title is very, it's very breaking. It says how nature works. Okay, so I'm sort of he's a god. Okay, so that's called the science of self-organization. Self-organized criticality can explain all the power law in nature. So you can check out the book. Okay, and so that's that. So that's one theory, one main competing theory, and another theory is called universality. So that borrowed from critical phenomenon. So as you know, if you have learned phase transition, you know that when a system undergoes a phase